Out in the open ocean, a machine taller than a skyscraper swings 3 blades across an area larger than several football fields, turning nothing but moving air into electricity for thousands of homes. Simple explanations make it sound almost trivial. Wind pushes the blades spin a generator, and power comes out. Yet that version leaves out the strangest truth about these machines. The real enemy of a giant offshore wind turbine is not too little wind. It's too much. Once violent wind enters the picture, the entire design stops looking like a giant windmill and starts looking more like an aircraft that has been forced to stand still on a pole in the middle of the sea. The machine that should not be standing. From a distance, an offshore wind turbine can look oddly delicate. A slim tower, a giant rotor, 3 impossibly long blades, and open water beneath all of it. That impression is misleading. The tower is supporting a massive rotating machine while waves, currents, and wind load the structure from different directions at the same time. Higher above the surface, the wind is usually faster and more consistent, which is exactly why engineers want these machines to be tall. Turbines do not just need wind in the abstract, they need access to a broad, relatively stable stream of moving air. Offshore locations often provide that advantage because there are fewer mountains, forests, and buildings disturbing the flow. Unlike a paddle that simply gets shoved backward by the wind, a modern turbine blade works much more like an airplane wing. Its curved shape creates lift, and that lift generates the force that turns the rotor. In other words, what looks like a giant propeller is actually an aerodynamic energy conversion system. Behind those blades, the nacelle contains the rest of the machine. Rotor motion turns a main shaft. That motion may pass through a gearbox or go directly into a direct drive system, and a generator converts the rotation into electrical energy. Power electronics then condition that electricity before sending it toward the grid. The sequence is elegant. Wind becomes lift becomes rotation becomes electricity. The invisible wall. Betz's limit. Imagine trying to extract energy from a river by blocking it completely. At first, that sounds efficient, but the moment you stop the flow entirely, the water can no longer keep moving through the system the way you need it to. Air behaves in much the same way. German physicist Albert Betz formalized this in 1919. A turbine must slow the wind down to take energy from it, but it cannot stop the wind completely and still operate efficiently. The theoretical maximum capture is 16/27 of the incoming kinetic energy, or about 59.3%. That creates one of the central paradoxes of wind engineering. A turbine that tries to take too much energy can become worse at taking energy. To manage that trade-off, the blades are not fixed in place. Each one can rotate around its own long axis, changing its pitch as wind speed rises. Instead of letting the rotor accelerate uncontrollably, the control system adjusts blade angle to keep output near the machine's rated level. When conditions become too severe, the blades can feather and the turbine can shut down entirely. Rather than simply collecting wind, the turbine is constantly negotiating with it. The ocean doesn't care how expensive your turbine is. Picture placing a skyscraper at sea, then adding salt water, waves, corrosion, shifting loads, and thousands of tons of machinery elevated high above the surface. That is the offshore wind challenge. On land, a turbine stands on a foundation that crews can inspect relatively easily. At sea, the same machine must transfer enormous forces through the tower, into a support structure, and ultimately into the seabed. For many fixed-bottom turbines, that support begins with a monopile, an enormous hollow steel tube driven deep into the ocean floor. Nothing in that load path gets to rest. Wind pushes the rotor loads the nacelle loads the tower loads the foundation, and the foundation pushes back through the seabed. At the same time, waves and currents are trying to move the structure in other directions. Engineers are not designing one isolated object. They are designing a chain of connected components that all have to survive the same assault. When the ground disappears farther offshore, the water becomes too deep for conventional fixed-bottom foundations to remain practical. At that point, the question changes completely. Instead of asking how to drive more steel into the seabed, engineers ask something much stranger. What if the turbine floats? That sounds absurd until you stop thinking of the tower as a standalone object. The turbine itself does not need to float independently. The entire support structure can be made buoyant. Mooring lines then connect the floating platform to anchors on the seabed, allowing controlled motion without allowing the whole system to drift away. Movement in this case is not necessarily failure. It is part of the design. A floating turbine is allowed to respond to the ocean, but only within limits that keep the machine stable enough to keep doing its job. The electricity has to escape. Even after the turbine produces electricity, the engineering problem is not over. That power has to travel down the structure, through subsea cables, across an offshore network, and eventually toward onshore infrastructure and the wider electrical grid. These are not underwater extension cords tossed onto the seabed. Offshore power cables have to survive pressure, temperature changes, seabed conditions, installation stresses, and in floating systems, the additional challenge of movement. The visible turbine is only the most dramatic part of a much larger machine. Hidden below the surface are foundations or floating substructures, mooring systems, anchors, export cables, electrical equipment, and a web of infrastructure that makes the whole project work. Calling an offshore wind farm a collection of turbines is technically true, but it badly understates what is really there. The power of size. Why make these machines so enormous in the first place? Because the power available in wind depends heavily on two things: wind speed and swept area. As blade length increases, rotor area grows with the square of the radius, which means longer blades allow the turbine to intercept a dramatically larger volume of moving air. Offshore conditions make that scale especially attractive. Big rotors can exploit cleaner, steadier wind, and a single very large turbine can potentially generate enough electricity to reduce the total number of machines needed in a project. Economically, that can be compelling. Bigger, however, does not mean simpler. Each additional meter of blade length adds weight, increases structural loads, raises demands on the hub and drivetrain, complicates transportation, and makes installation and maintenance harder. The industry is chasing a difficult balance. Larger turbines may reduce cost per unit of electricity, but only if the rest of the machine and the rest of the industry can keep up. The machine that is slowly being eaten. Salt water is ruthless. Offshore structures must deal with corrosion, moisture intrusion, fatigue, and mechanical wear in an environment that is expensive and difficult to access. Maintenance offshore is nothing like maintenance on land. A problem discovered dozens of kilometers from shore may require a vessel, a crane, a trained crew, and a narrow weather window before anyone can even reach the machine. During that delay, the turbine may be producing no electricity at all. Reliability, therefore, becomes just as important as raw output. A turbine is not valuable simply because it can generate power under ideal conditions. It has to keep generating power across years of harsh operation, and it has to do so without demanding constant rescue missions from shore. The turbine is constantly thinking. Inside a modern offshore turbine, control systems are doing almost as much work as the visible hardware. The nacelle can yaw so the rotor faces the wind. The blades can pitch to change aerodynamic behavior. The generator and power electronics regulate output. Sensors monitor loads, vibration, wind conditions, and machine health across the system. Think of balancing a broom vertically on your palm. You do not wait for it to fall and then react once. You make constant, tiny corrections: left, right, forward, back. A turbine operates on the same basic principle, except the broom is now hundreds of meters tall and the consequences of getting it wrong can cost millions. Brute force alone cannot protect a machine like this. Precision is what keeps it alive. The most dangerous wind isn't always the strongest wind. Many people assume the logic is simple. More wind means more rotation. More rotation means more electricity, and therefore stronger wind must always be better. That is only true up to a point. Once a turbine reaches rated output, the job shifts from maximizing power to limiting stress. Blade pitch changes, rotor behavior is controlled, and electrical output is held within safe bounds. In sufficiently extreme conditions, the turbine shuts down altogether. Modern machines are designed to feather their blades and stop operating near cutout wind speeds, which vary by design but are often around 25 meters per second or roughly 56 miles per hour. The crucial insight is this: the machine is not trying to survive maximum wind while continuing to produce at all costs. It is trying to recognize the moment when continued generation is no longer worth the structural risk. Fixed bottom versus floating. From the surface, a fixed bottom turbine and a floating turbine can look surprisingly similar. Both use a rotor, a tower, a nacelle, and the same fundamental process of turning wind energy into electricity. Below the waterline, though, they become entirely different machines. A fixed bottom turbine transfers loads directly into the seabed through its support structure. A floating turbine relies on buoyancy, mooring lines, and anchors to stay in position while still moving with the sea. That difference changes everything. Platform motion affects the rotor, the tower, the nacelle, the mooring system, and the cable design. Floating wind is not simply a matter of putting a turbine on a boat. It is the challenge of allowing a power plant to move with the ocean without letting that motion destroy the power plant. The failure that engineers can't ignore. Engineering projects do not live inside perfect equations. They live in real supply chains, real budgets, real weather delays, and real oceans. Steel prices change, interest rates rise, installation vessels become unavailable, construction schedules slip, manufacturing bottlenecks appear. Assumptions that looked solid on paper meet reality offshore and sometimes fail there. For that reason, the biggest turbine is not automatically the best turbine. The meaningful question is not how much electricity can this machine produce in theory, but how much reliable electricity can the entire system deliver over decades. Offshore wind is not a simple race toward size. It is an optimization problem involving cost, strength, manufacturability, installation, maintenance, and lifetime performance. The next problem: the ocean floor beneath every offshore project lies another engineering battlefield: the seabed itself. Water depth matters, but so do soil properties, geology, sediment movement, and currents. One of the less obvious risks is scour. As water flows around a foundation, it can erode material from the seabed and gradually reshape the support environment below the structure. That is why engineers may install scour protection, such as rock blankets, around fixed bottom foundations. Even the part of the turbine that seems most stationary is sitting inside a changing system. The ocean is always trying to modify the ground beneath the machine, and the design has to account for that. Why the blades are so strange? Look closely at a turbine blade and its proportions can seem impossible. It is incredibly long, relatively thin, and shaped differently from root to tip. Near the hub, blade must survive enormous structural loads. Farther out, the aerodynamic task changes, and the shape changes with it. Engineers are trying to create a component that is light enough to rotate efficiently, strong enough to survive repeated loading, and precise enough to produce useful lift across a huge swept area. Gentle-looking wind can still contain immense usable energy when a rotor is large enough. That is the hidden advantage of scale. The air does not need to look violent if the machine interacting with it is enormous. The humble object behind the giant machine. After all, the composite